Welcome to the Deep Dive, where we take a stack of information and really pull off the key knowledge for you. Today, we're diving into the world of stars, specifically star pairs. You might think a star is just a single dot of light up there, but actually, a huge number aren't alone. Many are in binary systems or even, more complex groups. So we're going deep into this incredible source, an essay by Michael Perryman. It focuses on a really groundbreaking catalog of resolved binary stars, all within about 1,000 parsecs. That's roughly 3,260 light years. So our cosmic neighborhood, basically, this whole catalog, it's built using data from the European Space Agency's Gaia mission. Think of Gaia as this ultra-precise 3D map maker for, well, billions of stars. And this isn't just about spotting double stars. It's really about unlocking secrets, how stars form, how they evolve, even how our Milky Way is put together. Okay, let's get into it.
Absolutely. And these systems, they're scientifically vital for so many reasons. I mean, understanding basic things like stellar mass, for one, but also probing, the galaxy's own gravity, the tidal field, through how these pairs might get disrupted over time. What's really fascinating, though, is just how complex it is to find them and study them. And this new catalog, it tackles that complexity head on. It's a major step.
Okay, so you mentioned their importance. Let's dig into that a bit more. Why exactly are binary stars such a big deal for scientists?
Well, they give us these unique windows into astrophysics, like understanding how stars form in the first place and then how they live their lives, their evolution. By watching them interact gravitationally, we can figure out fundamental things, especially their mass. That's way harder with a star just on its own.
Right.
And like I said, the really wide ones, they act like probes for the galaxy's gravity, its tidal field. That pull can actually tear them apart eventually.
Wow. And it sounds like they're not all the same either. Are we just talking two stars orbiting, nice and simple, or is it messier?
Oh, it's definitely messier. Huh. They come in this bewildering variety of setups. You've got your really close pairs, short periods that you can't even see as two stars directly. You need spectroscopy, looking for wavelength shifts, or photometry if one eclipses the other, causing dips in brightness.
Okay, the eclipsing ones.
Yeah. Then you've got the other extreme. Super wide pairs, long orbits, and even systems with 3, 4, or more stars in these complex hierarchical orbits. Different periods, different masses. It's like a whole zoo of configurations out there.
So with all that variety, finding them all must be incredibly tough. Is one instrument, even something amazing like Gaia, enough?
No, absolutely not. It's just impossible to catalog every type of binary, even just pairs with a single instrument. You really need a whole range of surveys,
Yeah.
spectroscopic ones, astrometric ones, measuring positions and motions super precisely.
Visual ones, too.
Visual ones, yes, for any kind of, complete picture. And this complexity, it makes measuring them with Gaia really, really tricky. I mean, a single star, okay, you need maybe 5 numbers, position, distance, motion over a few years. But binaries, multiples, they need way more data points over a much longer time, depending on how fast they orbit each other.
Right, that makes sense. So given those challenges, let's focus on this specific catalog we're diving into. It's from El Badri and colleagues using Gaia's early data release 3. What's special about this catalog? How do they actually build it?
Okay, first, their definitions are key, very specific. When they say binary, they mean systems with exactly 2 stars.
Okay.
They deliberately excluded anything more complex, like triples, because identifying those is a whole other level of difficult with this method.
Got it.
And resolved means Gaia actually sees 2 distinct sources, 2 separate identifiers in the EDR3 data.
So not the ones you can only spot by light dips or spectrum changes.
Exactly. It excludes those spectroscopic or eclipsing binaries we talked about.
Yeah.
It focuses purely on pairs where Gaia can literally see both stars as individual points.
That's a really important distinction. Helps narrow the search massively, I bet. So how do they sift through, well, everything to find these specific pairs?
So they started by grabbing all Gaia sources within that 1 kiloparsec distance limit, which means stars with parallaxes bigger than 1 milliarc second. And they wanted good quality data, so parallax uncertainty less than 20%.
Okay, and how many stars was that?
An absolutely colossal number, over 64 million sources.
Wow, 64 million. That's a lot of potential pairs to check. How do you even begin?
Yeah, it's mind-boggling. That it corresponds to something like 2 times 10 to the power of 15 possible pairings, just mathematically.
Unbelievable.
So from that massive list, they flagged initial candidates. They looked for pairs with a projected separation less than 1 parsec, any wider, and the galaxy's gravity probably breaks them up. And crucially, their parallaxes, their distances had to match up within 3 sigma, statistically speaking. And their proper motions, how they move across the sky, had to look like they were moving together in a bound Keplerian orbit.
Okay, so filtering by distance and shared motion, how many did that leave?
Still a huge number, about 100 million candidate pairs.
100 million.
Yeah.
Still sounds like finding needles in a haystack.
Yeah.
So this is where the really clever part comes in, right? Getting from 100 million down to the real deal.
This is where the really rigorous cleaning happens, because that 100 million, still full of chance alignments.
Stars that just look close from here.
Precisely. So they cleaned it by looking at each star's neighbors in phase space, which is like its cosmic postcode, combining its 3D position and its 3D velocity.
Okay.
They kicked out spurious pairs in really crowded areas, like toward the center of the galaxy or in the Magellanic Clouds. They eliminated overlapping pairs, which, interestingly, also removes genuine triple systems where two stars are too close for Gaia to separate, but the third is further out.
Ah, an unintended consequence.
Yeah. And they removed fake pairs found in open star clusters. All that cleaning got them down to just over 1.8 million pairs.
Okay, getting closer, but still not the final number you said.
Correct. There was one more step. They did further checks for chance alignments and calculated a detailed probability for each remaining pair actually being gravitationally bound. This probability depends on things like how far apart they are, where they are in the galaxy, how bright they are.
Makes sense.
And that resulted in their final sample, 1,256,400 binary systems, all with a high probability of being truly physically linked. It's a monumental data set.
Just incredible. 1.2 million high confidence pairs. So they built this amazing catalog. What did they learn? What do these binaries actually look like?
Well, the Gaia data, especially its multicolor photometry, combined with the distance from parallax, that let them place each star in the pair on the Hertzsprung-Russell diagram.
The HR diagram, right? The star's evolutionary map.
Exactly. So they could classify each star. Is it a white dwarf, that dense stellar remnant? Or is it a non-white dwarf, which usually means a main sequence star, like our sun, but it could also be a giant, a subgiant, even a young pre-main sequence star, or a brown dwarf.
And what kind of pairings did they find most often?
The overwhelming majority, 877,416 systems were main sequence pairs.
So two sun-like stars orbiting each other.
Basically, yes. That's the most common type they resolved. They also found over 16,000 systems with one main sequence star and one white dwarf, and about 13,390 systems where both stars were white dwarfs.
Double white dwarfs.
Yeah. Though it's worth remembering, about a quarter of the stars didn't have color data in this specific Gaia release, EDR3.
Right. Okay, what about other physical things, like how far apart are they typically, or how bright do they look to us?
Their angular separations, how far apart they appear on the sky, range from really close, 0.2 arcseconds, all the way up to a full degree.
Wow, a degree is huge.
It is. But the peak, the most common separation, was around 1.2 arcseconds. Brightness-wise, the median magnitude for the primary star, the brighter one, is G15.2. The secondary is typically fainter, G17.7.
Faint.
Yeah, pretty faint. And white dwarfs, much fainter still. For those double white dwarf systems, the median magnitude was around G19 for both stars. Incredibly hard to spot.
Definitely need powerful telescopes.
Yeah.
And where are these systems generally located? Are they spread out evenly?
The median distance for the whole high-confidence sample is 485 parsecs, so relatively nearby, cosmically speaking. But the systems with white dwarf pairs and the white dwarf main sequence ones, they're intrinsically fainter.
So that you can't see them as far away.
Exactly. So their median distances are closer, 148 parsecs and 212 parsecs respectively, and those seem to be spread pretty uniformly across the sky. But the main sequence pairs, which dominate the sample and reach further out, they clearly show the structure of the galactic disk. Most are concentrated in that flat plane where most stars live.
The Milky Way structure imprinted on the data.
Pretty much. Most are kinematically part of the disk population, though they did find a few thousand that seem to belong to the galactic halo, that sparse region surrounding the disk. Oh, and they also cataloged about 10,000 pairs where the primary is a giant star. About half of those giants are in what's called the red clump phase of evolution.
Okay.
And there are about 130 giant pairs and maybe 13,000 where one star is a subgiant, just starting to evolve off the main sequence.
So, taking all this together, what does it tell us about how common these wide binaries are, say, in our local patch of the galaxy?
Well, they calculated the total space density for wide binaries, ones separated by more than 30 astronomical units, so wider than our solar system roughly.
Okay.
And they found it's about 0.0006 per cubic parsec, plus or minus 0.001 in the solar neighborhood.
How does that compare to just all stars?
It's about 1/10 of the density of all unresolved Gaia sources nearby. That density is more like 0.07 per cubic parsec. So wide binaries are a significant fraction, but still, a fraction. But in terms of numbers, this catalog is a massive leap. It gives us about 4 times more high-confidence binaries than previous Gaia releases, and it absolutely dwarfs older catalogs. Like the Washington Double Star catalog, a major reference point, had maybe 141,000 entries back in 2017.
Compared to 1.2 million now.
Exactly. It's a completely different scale, a real game changer for studying these systems.
Okay, now this is fascinating. I saw something in the source material about twin binaries. What's the story there? Why are they special?
Ah, yes, the twins. This is a really interesting puzzle astronomers have been chewing on. The question is, why do we see this apparent excess of binary pairs where the two stars have almost exactly the same brightness, which presumably means they have almost exactly the same mass, these twin binaries?
It's not just random pairings.
It seems not. This isn't totally new. It's been hinted at before. But an earlier study by El-Bedri, also using Gaia data, really nailed it down. They found this sharp, statistically significant excess of equal mass twins. And intriguingly, it extends out to really wide separations, thousands of AU, depending on the primary star's mass.
So what did this newer, bigger EDR3 sample show?
Yeah.
Did it confirm the twins?
Yes, it strongly confirmed it. And it showed the excess is really quite narrow. You see a steep jump in pairs where the mass ratio is between 0.95 and 1. So almost identical masses.
Really close.
Yeah. But below that, say a 0.9 mass ratio, no significant excess. It really focuses on the twin characteristics.
So if these wide twins are definitely a thing, what does that imply about how they form? Does it mess with the standard theories?
It does make things more complicated, yeah. The existence of twins out at these wide separations is actually pretty hard to explain with the simplest formation model. The model is called core fragmentation, basically. A collapsing cloud of gas just breaks into two pieces that become the stars. That process doesn't naturally produce so many identical twins, especially ones that end up so far apart. So the thinking now, the conjecture, is that these wide twins probably didn't start wide. They likely formed much closer together, maybe less than 100 AU apart. Perhaps by pulling in material, accreting from a disk of gas and dust surrounding both young stars, a circumbinary disk, that might help equalize their masses.
And then they got pushed apart.
Exactly. They were then subsequently widened, flung outwards by chaotic gravitational interactions with other stars within the crowded environment of their birth cluster.
Wow. Okay. A much more dynamic history. So this catalog isn't just a list of stars. It's a tool, right?
Yeah.
What does this unlock for astronomers? What can they do with 1.2 million high-confidence pairs?
Oh, it's incredibly valuable. It's going to be used in tons of ways. It's like a precision toolkit for astrophysics. For example, calibrating stellar ages. That's a big one. If you can figure out the age of one star in a binary pair.
Then you know the age of the other one, too.
Exactly. They formed together. So even if the second star is in a weird evolutionary phase, or one that's hard to age directly, its twin gives you the answer.
Clever.
It's also crucial for pinning down the relationship between a star's initial mass when it formed and the final mass of the white dwarf it leaves behind. Because in these pairs, you often have a white dwarf with a main sequence companion whose properties you can measure well, constraining the system's history.
Okay, that makes sense. What else? I imagine there's more.
Oh, absolutely. It helps derive white dwarf masses in another way, too, using gravitational redshift.
Right.
That's this tiny shift in light caused by strong gravity. You need a reference point, and the companion star provides it.
Because they should have the same velocity through space, basically.
Precisely. They should share the same radial velocity. The catalog also lets scientists study the chemical makeup, the abundances of the stars that became white dwarfs, which can even give clues about planets that might have fallen into the white dwarf we know that happens.
Whoa. Debris from disintegrated planets?
Yep, it's a known thing. You see the chemical signatures. And you can investigate spin alignment. Are the twin binaries spinning in a more aligned way than non-twin pairs? That tells you about their formation and history.
So many angles.
Yeah, and even for calibrating big spectroscopic surveys, if you assume stars in a wide binary have very similar chemistry, you can use them to check for subtle errors or biases in the survey measurements.
That's really useful. And finally, you mentioned earlier they probed the galaxy itself. not just the stars.
Yes, they're fantastic dynamical probes, especially the really wide ones. At those large separations, they become sensitive to gravitational kicks from passing stars or giant molecular clouds.
They can get disrupted.
They can. And the rate at which they get disrupted, or how wide they can survive in different parts of the galaxy, tells us about the gravitational environment, the density of stuff, the history of encounters. They're like little gravitational test particles scattered through the galaxy.
What an incredible deep dive this has been. Just amazing. We've seen how Gaia and this really meticulous analysis have produced this just unprecedented catalog of resolved binary stars. It's the largest ever, by far. And from understanding how stars live and die to mapping the galaxy's own gravity, these stellar pairs are unlocking so many secrets.
Absolutely. This catalog is a profound step forward. It really sharpens our ability to use binaries as these precision astrophysical tools. The insights we're getting, especially into how they form, how they evolve, how they interact, and that whole fascinating puzzle of the twin binaries, it's really pushing the frontiers of our understanding.
So next time you're looking up at the night sky, maybe at a star that looks perfectly single, just pause and consider. Maybe it's locked in this intricate cosmic dance with a hidden partner. Or maybe it has a long-lost twin, flung far away, but still sharing a common origin story across the vastness of space. What other stories, what other fundamental truths about our universe might be waiting to be revealed just by carefully studying these astronomical pairs? That's all for this deep dive. We hope you feel a little more informed and maybe just a little more curious about the cosmos. Until next time.